Imagine we have two springs facing each other, and in between them is this rougher patch of surface which has friction. All of the other parts of the floor are frictionless, and there's this block here against the first spring. We're going to take this block and push it to the left, causing the spring to compress from its relaxed length. Now we release this thing from rest, and what happens? It accelerates, slows down over the rougher patch, and then slows down as it compresses this other spring. Now we know that if we watch this a little bit longer, then eventually the block will push back to the left, and maybe it'll bounce back and forth a few times, but let's forget about that part and consider only up till this moment when the block stops right before firing back off. To analyze this situation, we'll need some values, but let's not worry about those just yet. First, consider the energy transformation equation. This equation says that the total mechanical energy at the initial moment on the left is equal to the total mechanical energy at the final moment here on the right. Now, this equation would be true if we didn't have friction. But the friction here disrupts the equation. We will have to modify this equation to account for the friction. But before we go to that step, let's just evaluate the energies present here at the beginning. Okay, we released the block from rest, so does it have kinetic energy? No. Does the block have any gravitational potential energy? No, because it doesn't have height off the ground. All it has initially is this elastic potential energy stored in the spring. At the final moment, do we have speed? Well, no, because it stops right before firing off. Is there any gravitational potential energy? No, we're still on the ground. So all we have at the end is this elastic potential energy again. Let's simplify the equation. Now it's time to fix the equation because friction is present and friction takes energy out of the system. So the initial amount of energy has to get something subtracted away to give us the total energy at the end. Friction does negative work, so we subtract this term for friction's work, and we've learned already why this is the equation for work by friction on a horizontal surface. Well, can we solve for the distance d? Let's look. We have the spring constant k for the first spring and also for the second spring, so we know both of those values. We have the initial compression for the first spring. We'll have to convert that to meters. We have the final compression for the last spring, 3 centimeters, which we also convert to meters before plugging in. We know the coefficient of kinetic friction. We know the mass of the object. We would have to convert that to from grams to kilograms. We know g is 9.81, so we could solve for distance. Let's look at another scenario. We have a block that we push to the right with some rightward velocity, but then it slows down and stops as it crosses this friction surface. So here we go. Okay, we can add some values and analyze the energies that are present at the beginning and the end. Here's the mechanical energy conservation equation, but again, it's not correct because it fails to account for friction. Before we add in the piece from friction, let's evaluate the energies we have here at the beginning and at the end. Initially, we give the object speed. Does it have height off the ground? No, so there's no gravitational potential energy. Is there any compression of a spring at the beginning? No. Do we have any speed at the end? Well, no, it stops. There's still no height off the ground, and there's no spring at the end. So this simplifies in kind of a strange way. There's no energy left at the end, and the system has lost all of its energy. So clearly this is an incorrect equation, and we have to add something here to account for the negative work by friction. We plug in that formula for the negative work by friction. Again, mu times the normal force, which balances mg, gives us the friction force. And we multiply friction by distance to get work, making it negative, of course, because the friction force is opposite the distance. So can we solve for the distance traveled across this rougher patch? Let's find out. We know the mass, but we have to convert that to kilograms, and mass shows up twice. We know the initial speed, which is 4. We know the coefficient of friction, which is 0.3. G is 9.81. So yeah, we can solve for distance. We have a single equation with one unknown. Time for a pop quiz. Let's take a very similar scenario, except now we have a spring involved. So we push this block backwards and we release from rest. The block fires off, travels across the rough surface, and stops after going some distance d on that rougher surface. My question for you is, what's the equation that we write down? How is it different from this scenario? Remember that the block starts from rest, so it doesn't have kinetic energy at the beginning. Instead, all we had was elastic potential energy. But there's no energy left at the final moment right here. So friction, which was on a horizontal surface here, friction must have taken away all of this initial energy, leaving us with nothing at the end. On to our next scenario. We give this block some rightward velocity. It slows down over the rough patch, and then it stops here on this ramp at some height h before falling back down. Now, if this is the highest point the block achieves, then it stops right here before going back down. So let's evaluate the energies present, and we've added some values. And of course, we'll start with the same equation we've seen for every scenario. Initially, do we have speed? Yes, we do. Do we have gravitational potential energy? No, because there's no height off the ground. Do we have any elastic potential energy initially at this moment? No, because there's no compression of a spring. At the end, do we have speed? No, so there's no kinetic energy. We do have height because we're elevated above the ground, but do we have elastic potential energy at the end? No, there's no spring involved. So we simplify, and then we add in the effect of friction, which is negative work that subtracts away from the initial energy. Notice we do have a ramp involved, but there's no need for the cosine of the ramp angle because the friction only acts on this horizontal surface. So on that horizontal surface, the normal force is mg, not mg cos ramp angle. So can we use this equation to find the height the block achieves? Let's look. We have the mass, which appears 3 places. We don't need to convert it because it's in kilograms already. That's what we want. What about the speed? We have that as well, the speed at the beginning. We know mu is 0.6. We know g is 9.81. The distance across the friction surface is 2 meters. We have this g as well. So we can solve for height. We have a single equation with one unknown. All right, now let's tackle something that's pretty similar, but a little bit harder. You can see already that friction acts at this incline. Okay, we have a spring, we push the block backwards, and we release from rest. The block goes forward, and it slows, and it stops right here at the top before falling back down, perhaps. Let's put some values in a moment, but first, just evaluate the energies present. Did we have kinetic energy here? No, because there was no speed. Did we have height at the beginning? No, so no gravitational potential energy. There was compression, so we had elastic potential energy, and we're done with the left side, the initial moment. Turn your attention now to the final moment. Is there speed? No, so there's no kinetic energy. We do have height, so there is gravitational potential energy, but the compression is 0 at this point because the spring is not compressed at the end. It has released, causing the block to fly up. So we simplify the equation, and we're going to move this over to make room. And now we have to add in the effect of friction, which is to subtract some energy from the initial amount. This time, the equation for work by friction looks a little different. And the reason it looks different is because the friction occurs on this incline. So the angle theta here is the ramp angle. It's not the angle between force and distance. What's the angle between the friction force and the distance? Where did that cosine theta go? Because apparently there's two cosine thetas. Oh yeah, the friction force is 180 degrees from the distance, and cosine of 180 is -1. That's where this negative comes from, and that's where the first cos theta goes. This cos theta is part of the normal force. On an inclined plane, mg cos theta, where theta is ramp angle, mg cos theta is the normal force. We'd multiply that normal force by mu to get force of friction. So really, right here, we have force of friction, distance, cos 180. That's the equation for work. Okay, that was a little long-winded, but it's nice to review. Let's add in some values and see if we could solve for the distance the block travels up the ramp. We know the spring constant, that's in the unit that we want. We know the compression distance, but we have to convert it to meters. We know the coefficient of friction, 0.156. The mass is 1.1 kilograms, shows up twice in the equation, and kilograms is the unit we want, so no need to convert. G we know, that's 9.81, and it shows up twice. Theta we have, that's the ramp angle, and we're looking for distance. But what about the final height? Is that a second unknown in this equation? What can we put here? Well, look at the right triangle we have. This final height is simply the opposite leg of the right triangle. So it's equal to hypotenuse sine theta. Let's remove h final and put hypotenuse sine theta. This is a clever trick because it allows us to put in just a single unknown in this equation. So we have simplified to the point where we could solve. For all of these different scenarios we've seen, we used the same method. Here it is. We started by analyzing the initial energy present and the final energy present. To do this analysis, we looked for speed, which indicates kinetic energy. We looked for height, which indicates gravitational potential energy. And we looked for compression of a spring, which indicates elastic potential energy. Once we figured out what was present, we simplified that crazy big equation and made anything zero that we could. Then we accounted for the negative work by friction, which was either negative mu mg times distance for a horizontal surface, or for an inclined surface, we just add in cosine of the ramp angle. Then we looked for tricks. And the only real one we've seen is that the height, either at the beginning or the end, could be equal to d sine theta if you're on a ramp, and if the friction surface is part of the ramp. Finally, we plugged in the known quantities that were given, and we converted as needed, and we solved for the unknown quantities. Remember that when you plug quantities into the equations, nothing should have a prefix, nothing should have kilo or centi or any other prefix, except for mass. Mass is the only one we plug in with a prefix. You want your mass to be in kilograms before you plug in. So don't forget to convert. Thanks for watching.